This is Module 1, Lesson 22, Solution Sets to Simultaneous Equation. So the opening exercise says consider the following, compound sentence. X plus y is greater than 10 and y equals 2x plus 1. Part A says circle all the ordered pairs that are solutions to the inequality. So let's first look at these solutions and see if they are solutions to the inequality. So 3 in place of x, so this would be 3 plus the y 7 is greater than 10. Is 10 greater than 10? No, it's not, so we can't answer that one. The next pair is 7 plus 3. So again, we have 10 is greater than 10, which is not true, so that's also not a solution. The next pair is negative 1 plus 14 is greater than 10. Negative 1 plus 14 would be positive 13, which means this is a solution. The next order pair is 0 and 1. 0 plus 1 is greater than 10. That is not true. 12 plus 25 is greater than 10. That is true. 5 plus 11 is greater than 10. That is true. Zero plus 12 is greater than 10. That is true. 1 plus 8 is greater than 10. That is not true. 12 plus 0 is greater than 10. That would be true. And negative 1 plus negative 1 is greater than 10, which would really be negative 1 minus 1, which is negative 2, and negative 2 is not greater than 10. So now we have located all the solutions, or all of these solutions that are all the ordered pairs that are solutions to the inequality. Now let's look at part B. Underline all the ordered pairs that are solution to the equation. So again, let's plug in these ordered pairs to see if they make a true statement or not. Starting with 3, 7. So 7 is the y, so 7 equals 2 times 3 plus 1. 2 times 3 would be 6. And 6 plus 1 would be 7, which is a true statement. So that works. Let's do the same thing with the next pair. Y is 3 equals 2 times 7 plus 1. 2 times 7 would be 14, plus 1 would be 15. That is not a true statement, so we do not underline that one. So for the next pair, negative 1 comma 14. So 14 is the y equals 2 times negative 1 plus 1. 2 times negative 1 would be negative 2 plus 1 is negative 1. That is not a true statement. Zero comma 1, so 1 is the y. 2 times 0 plus 1. 2 times 0 would be 0. And 0 plus 1 is 1, so this works. The next y is 25 equals 2 times 12 plus 1. 2 times 12 is 24. 24 plus 1 is 25, so this works. $11 equals 2 times 5 plus 1. 2 times 5 is 10. 10 plus 1 is 11. $12 equals 2 times 0 plus 1. 2 times 0 is 0. And 0 plus 1 is not 12. $8 equals 2 times 2, wrong x. 2 times 1 plus 1. 2 times 1 is 2. And 2 plus 1 is 3. That is not a true sentence. Zero equals 2 times 12 plus 1. 2 times 12 is 24. 24 plus 1 does not equal 0. And the last one, negative 1 equals 2 times negative 1 plus 1. 2 times negative 1 would be negative 2. And negative 2 plus 1 is negative 1. Part C of the opening exercise asks us to list the ordered pairs from above that are solutions to the compound sentence x plus y is greater than 10 and y equals 2x plus 1. So they're asking us to locate the solutions that were true for both of those, not just one of them, but both the inequality and the equation. And if you look at our set, the only ones that we have circled in underline are 1225 and 511. Part D. List 3 additional ordered pairs that are solutions to the compound sentence. So again, they're asking us to find additional ordered pairs that are solutions to not just the equation and not just the inequality, but that are true for both of them. So one might be when we plug in 4 for x. So let's see, if I plug in 4 for x, what would my y be when I solve for this? I would subtract 4 on both sides, and I would be left with y is greater than 6. Okay, so it looks like 4, 6 is going to work. But now let's see, make sure it's true for the equation. 6 equals 2 times 4 plus 1. 6 equals 8 plus 1. 6 equals 9. Well, that's not a true sentence, which means 4, 6 is not going to work here. So let's look at the equation and see if there's another way we can look at it. This time, let's try still using 4, but let's plug it into the equation first. 2 times 4 plus 1. That would be 8 plus 1, so that would be 9. And let's see if this works now for this. We know our y is 9 based on the equation. And is 9 greater than 6? Yes. So 4, 9 will work. Let's plug in 6. Let's plug in 6 and see what we get from 6. It's much easier to plug into the equation versus the inequality because the inequality has a range, so to speak, right? This is all values greater than 6, where the equation is just going to have one value that typically works. So we plug in 6, let's plug into the equation first. So y equals 2 times 6 plus 1. So y would equal 12 plus 1, which would be 13. So let's see if 613 works. So let's plug it in here. X plus y is greater than 10. 6 plus 13 is 19. That is a true statement. So 613 does work. And let's plug in 8. Let's plug in 8, see what we get with 8. So again, let's plug into the y. Y equals 2 times 8 plus 1. 2 times 8 is 16 plus 1. That would make 17. So it looks like the coordinate pair 8, 17 would work. Now let's make sure it works or holds true for the inequality. X plus y is greater than 10. 8 plus 17 is 25. And 25 is greater than 10, which means 817 works. So here is three additional solutions to this compound sentence. Again, meaning that they are both true for the inequality and equation. Yes, there could be many others that work for this, not necessarily those specific three. Let's look at part E. Part E says sketch the solution set to the inequality x plus y is greater than 10 and the solution set to y equals 2x plus 1 on the same set of coordinate axes. So last week we looked at how to graph just the inequality and how to graph just the equation. And so today we're going to look at how to graph both of them on the same axis. Okay? We still take the same steps, so let's first start with this equation here. And remember, in order to graph the equation, it has to be in slope-intercept form. And slope-intercept form is y equals mx plus b. So we always want to start with our b because our b is our y-intercept. So in this case, it's 1. So we're starting at 1. And my slope is 2. It's positive 2. So from this purple dot, I'm going to go up 2 and over 1. I'm going over 1, remember, because we always graph slope as a fraction. And the top number tells us whether we're going up or down. And the bottom number tells us how many we're going to the right. And then from this dot, I keep going. Now let's look at the inequality. Again, just like the equations, it has to be in slope-intercept form first. So, how would I get y by itself here? I would have to subtract x. So now I'm left with y is greater than negative x plus 10. So again, I start with my y-intercept, which is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that top dot. And my slope is negative, and if there's an understood 1 there. So negative 1 over 1. Which means from this red dot, I'm going down 1 since it's negative, and over 1. Down 1, right 1. Down 1, right 1. Down 1, right 1. Down 1, right 1. And so on and so forth. So remember with inequalities, we have dotted and we have solid lines. And so since this symbol is greater than, there's no bar underneath, this would be a dotted line. Dotted or dashed, however you look at it. And my symbol is greater than, which means when it comes to shading, this means I need to shade above the line, greater than. So above this line would be all pink. So when I look at how I graph the inequality and how I graph the equation, the only points that lie in both solution sets here would be this part of the axis right here, this part of this line, because it happens to fall on both the line and it happens to fall in the shaded region. So how would I describe the solution set to this inequality and equation? All the points that lie on the line, so on the equation, and above the inequality line. So again, this is a system, which means that we have to find solution sets that are true for both, not just one of them. let's look at example 1. Solve the following system of equations. So we're first going to look at an algebraic way. And this algebraic way we're going to refer to as the substitution method. Some important things to remember and to know about the substitution method is that you first have to solve for a variable. So if we look at our system, the top equation is solved for y, which is perfect. So the first step is already done for us. The second step is to substitute that expression into the other equation, where we see that variable. So for example, this is y equals this, so all of this in the parentheses is y. So I'm now going to substitute that into the place of y here. So if I write that out, I'm going to rewrite my bottom equation. So I've got x minus, anytime we substitute something we want to put in parentheses, 2x plus 1 equals 7. So this says x minus y equals 7, and I'm substituting that for y. So now let's simplify this. So I've got to distribute my negative first. So I've got x minus 2x minus 1 equals 7. Combine like terms. 1x minus 2x would be negative x, or negative 1x. And if I add 1 to both sides, I've got equals 8. And then I would divide by negative 1. So x would equal negative 8. And we have an x, and now we need to solve for y. So the last step is to plug in solve value, or solve variable, to find the other value. So it does not matter which equation that you use when you plug negative 8 back into. But I'm going to plug into the top one because I'm a creature of habit. Y equals 2 times negative 8 plus 1. Y equals, this would be negative 16 plus 1. So y equals negative 15. So we write this as a solution, aka as an ordered pair. So my solution is negative 8, comma, negative 15. X, comma, y. Now let's look at how to solve this graphically. So remember, in order to graph something, it has to be in slope-intercept form. So the first equation they gave us was y equals 2x plus 1, which is already in slope-intercept form. So again, I'm going to start at my y-intercept, which is 1, and my slope is 2. So up 2 over 1, up 2 over 1, and so on and so forth. Similarly, I could also go for my y-intercept. I could go the opposite way and still be on this line. So instead of going up 2 over 1, I can go down 2 to the left 1. You see how that still would fit on the line? And my other equation they gave us in the last problem was, or the same problem, excuse me, it's on the other slide. X minus y equals 7. Now this is not in slope-intercept form, so I cannot graph it yet. So I have to isolate y, which means I need to subtract x. So I'm left with negative y equals negative x plus 7. Divide by negative 1 all the way across. Y equals positive x minus 7. So my y-intercept is negative 7. And I have I have a positive slope. So up 1 over 1, up 1 over 1. And remember, you can do the same thing. You you can go the opposite way. Down one to the left one. So if you'll notice here, it looks like we are eventually going to cross lines. So let's go back to our red line and see if we can keep going. So from this red line, remember my slope was 2. And now let's go back to my blue line and see if I can get this one over. And so when you graph this, you will eventually see that these two lines will cross at our solution. And our solution was -8 and -15. So if you look, we didn't actually hit it yet, but we will. Thus, the solution that you get algebraically, you will also get graphically. So graphically, the solution is where the two lines intersect. Exercise 1. Solve each system first by graphing and then algebraically. So let's do algebraically for, actually this says first by graphing. So look at our top equation. Actually both equations here are already in slope-intercept form. So let's go ahead and graph these. So I've got y equals 4x minus 1 and y equals -1/2 x plus 8. So my y-intercept of the top equation is -1, and my slope is +4. So up 4 over 1, up 4 over 1, just like I can do it backwards. Down 4 to the left 1. Now let's look at the other one. Our y-intercept is 8, which is right at the top there. And my slope is -1 over 2. So -1 over 2, -1 over 2, -1 over 2. And if I keep going, my line kind of missed that red dot there for a second. But if you see here, we have a red dot and a blue dot at one point, which means this is our solution. It's where the two lines intersect. And that coordinate pair is 2, 7. 2, 7 is that coordinate pair. So our solution is 2, 7 to this system. So now let's see if we can get that algebraically. So remember, in order to solve via substitution, one of them has to first be solved for a variable, and in this case it is. We get a y value. So if I substitute this in where the y is, it is out front. So I've got 4x minus y equals -1/2 x plus 8. Because it is y equals y, essentially here. Let's combine like terms. So if I add 1/2 x to this 4, and I add 1 over here, those are going to cancel, those are going to cancel. So I'm left with 4.5 x equals 9. And when I divide by 4.5, I get x equals 2. So I'm on the right track. And now let's plug in my x value to get the y. Y equals 4 times x, we just solved for x, minus 1. 8 minus 1 is 7. So my solution is 2, 7. So as a reminder, when you go to plug back in your x value, it does not matter which equation that you use. So if you'll notice, our solutions match 2, 7, 2, 7, which they should. No matter how you solve a system, you should get the same solution. Let's look at part B. So again, let's graph them first. So the first one was 2x plus y equals 4. And you can't graph unless it's in slope-intercept form. So let me subtract 2x on both sides. So now I've got y equals negative 2x plus 4. So this one's in business. Let's go ahead and graph this. Y-intercept of positive 4. Slope of negative 2. So down 2 over 1. Similarly, I can go for my y-intercept and go the opposite way. Up 2 to the left 1. You'll see it kind of fits on that graph still. Now let's look at my other equation they gave me. 2x plus 3y equals 9. Let's isolate the variable y. So I've got 3y equals negative 2x plus 9. And now I'm going to divide by 3. So that leaves me with y equals negative 2/3 x plus 3. So my y-intercept is positive 3. I have a slope of negative 2/3, so I'm going down 2 over 3. Down 2 over 3. Similarly, I could go up 2 over 3. So you see here that my lines cross. But do they cross at a specific point? No. If you look carefully, they cross right there in the middle. So it's going to end up being a fraction of some sort. So let's see what we get algebraically first and make sure that aligns. To solve via substitution, remember we have to isolate the variable. It doesn't matter which variable you isolate. So if we look at this top equation, y is already by itself in a sense because it has a coefficient of 1 versus the x that has a coefficient of 2. So let's solve for y, and in fact we already did, because if we solve for y, it's really in slope-intercept form, and we know that is y equals negative 2x plus 4. So now we know that this is y, so let's plug this whole thing in where we see y. 2x plus 3 times our y that we just found equals 9. Simplify and distribute. 2x plus, really that would be a minus 6x plus 12 equals 9. Combine like terms. 2x minus 6x would be negative 4x. And if I subtract this 12 on both sides, I'm left with equals negative 3. Divide by negative 4 on both sides. X equals positive 3/4. So I did get a fraction, which is good. Now let's plug in my x value to find my y. Again, it doesn't matter which equation you use. I'm going to use the top one as a habit. So 2 times 3 over 4 plus y equals 4. So 2 times 3/4 would be 6 over 8, which can be reduced to 3 over 2 plus y equals 4. When I subtract 3 halves on both sides, I'm left with y equals 5 halves. So my solution is 3/4, 5 halves. So 3/4 is 3/4, so it's around 0.75. And 5 halves is 2.5. So let's look at my graph and see if this matches. So around 0.75, 2.5. So almost 1 and 2.5. So that is correct. So graphically and algebraically, we got the same solution. So if you'll notice, the graph sometimes only gives us an approximate solution here. It will be very difficult to give a correct answer. You might be close, but it would be very difficult to give a correct and specific example. So sometimes solving by graphing only yields an approximate solution. Now let's look at part C. Again, let's solve this graphically first. So my first equation is 3x plus y equals 5. I have to get this in slope-intercept form first, so I'm going to subtract 3x on both sides. And I'm left with y equals negative 3x plus 5. Now I'm in slope-intercept form. My y-intercept is 5. My slope is negative 3, so I'm going down 3 over 1. Just like I could go up 3 over 1. Sorry. Now let's look at my other equation. 3x plus y equals 8. So again, I have to get this in slope-intercept form first. So I subtract 3x. And now I've got y equals negative 3x plus 8. So I got a y-intercept of 8, which is up top. And same slope, down 3 over 1. So does it look like these lines are graphing? Or, excuse me, does it look like these lines are intersecting? No. And we know they're not going to intersect because their slope is the same. And since they do not intersect, we do not have a solution, which means our response is no solution. So this can be true for any system where the slopes are the same. Anytime you have the same slope, it's no solution. And when you have lines that have the same slope, they look like parallel lines, which is what we have here. They look like railroad tracks. So now let's make sure we get the same solution algebraically. So again, remember we have to solve for a variable first. And in this case, it would be easier probably to solve for y, since again it already has an understood coefficient of 1. And we've actually already solved for y. It was y equals negative 3x plus 5. Which means this equals y, which means we're going to plug this in where we see y. 3x plus negative 3x plus 5. This time we have a positive out front, so we really don't have to distribute anything. So 3x minus 3x would be gone. So we're left with 5 equals 8. So our variables cancel, which means we have to decide whether or not it's a true or false statement. And this is a false statement, which means our response is no solution. So as you see, our solutions do in fact match. Now let's look at example 2. The question is, now suppose the system of equations from exercise 1, part C, was instead a system of inequalities. Graph the solution set. So first of all, note that the directions don't ask us to solve it algebraically. They ask us to just simply graphically solve this. And we have inequalities. And just like equations, we first have to make sure that they are in slope-intercept form, which means we need to subtract 3x on both sides to get y is greater than or equal to negative 3x plus 5. Just like this one would be y is greater than or equal to negative 3x plus 8, because I had to subtract 3x from both sides on both equations, actually. So now let's graph them. Let's graph the top one first. I've got a y-intercept of positive 5, and my slope is negative 3, down 3 over 1. My inequality symbol is greater than or equal to, which means I have a solid line. It's not dotted, it's a solid line. And I'm shading above. But before I shade above, I'm just going to draw myself some arrows. I'm going to come back to the shading part at the end. You don't want to shade until you graph both inequalities. And let's graph the other one. I've got a y-intercept of 8. My slope is the same, down 3 over 1. And it's a greater than or equal to symbol, which means it is a solid line. And my symbol is, oh, I wrote the wrong symbol. Huh. You see that? Less than or equal to versus greater than. So this should be really a less than or equal to. I don't know why I flipped that. Less than means I'm going to shade below the line. So if I have to shade above the purple line and below the red line, if you'll look carefully, it's just going to be the space in between that I'm shading. Because my solution set has to fit for both of them. And it has to be greater than the top equation, so greater than the purple line, and less than the red line. So it's this shaded spot in between. So the solution to a system of inequalities is where the shaded regions intersect. Now let's look at example 3. Graph the solution set to the system of inequalities. So similar to the last problem, and remember, in order to graph, we have to have it in slope-intercept form. So I'm going to subtract 2x on both sides. So now that leaves me with negative y is less than negative 2x plus 3. I have a negative variable, so I've got to get rid of that. So now I have y, I divided by a negative, which means I have to flip my inequality symbol. And now I'm in slope-intercept form. So let's go ahead and graph this one. A y-intercept of negative 3. My slope is positive 2. Up 2 over 1. Just like I can go down 2 to the left 1. My symbol is greater than. There's no bar, which means I have a dotted or dashed line. It's greater than, which means I need to shade above the line. So above the line would be this direction. So again, I'm not going to shade it until I've graphed the other inequality, which means I need to subtract 4x. So now I'm left with 3y is greater than or equal to negative 4x plus 0, which you don't have to write the plus 0. Now I'm going to divide by 3. I am dividing, but I'm not dividing by a negative. So you keep the sign, and that negative 4/3 x. So my y-intercept, I don't have one. Okay, it's an understood 0. So I'm starting at 0, 0, and I'm going down 4 over 3. Down 4 over 3. My symbol is greater than or equal to, so it's a solid line. And it's greater than, which means I'm going to shade above said line. So look carefully at your lines and look carefully at your arrows in which you indicated which way we're shading. I have to go above my red line and above my blue line. So the only place that this works is this section all in here. Because it has to be above this line and above this line. And if you look at our arrows down at the bottom, we can't shade anything there because it has to be above that red line and above that blue line, and there's nothing in common there. So again, as a reminder, the solution set to a system of inequalities is where the shaded regions intersect. So any point in this black shaded region is a solution to this system of inequalities. Exercise 2, Part A. Graph the solution set to each system of inequalities. So again, we have to get it in slope-intercept form first, which means we need to subtract x from this top equation, so we're left with negative y is greater than negative x plus 5. Get rid of that negative. So I'm dividing by a negative, which means I need to flip my sign. Positive x minus 5. Go ahead and graph this one. Y-intercept of negative 5. Slope is positive 1. It's less than, there's no bar underneath, which means it is a dotted line. And let's look at my other inequality. X is greater than negative 1. So if you'll notice here, I don't have a y, and that's completely fine. Look at your x values. You know x, this is the x-axis here, okay? And this is the y-axis. So the line x equals negative 1 would be this line right here. This is x is negative 1 right here. So we are going to look at your symbol. X is greater than. There's no bar underneath, so we're going to draw a dotted line all the way down where x is negative 1. And that does not look so dotted, does it? That's better. So now let's go back to our shading. So this last one that we just graphed, x is greater than negative 1, which means it would be to the right of this line. So anything to the right of this line. And if you look at our other line, y was less than, I shouldn't underline that because you can probably think that. Y is less than that line. So below that line, lower. So anything to the right of this line here and less than this line would be all of this section right here. And beyond. Because it has to satisfy to the right of this vertical line and below that other line. Use your symbols to know which way you're shading. Part B, this time we have 3, and that's perfectly fine. The top one's already in slope-intercept form, so we can go ahead and graph that. Y-intercept is positive 4, slope is positive 1. Up 1, over 1. Up 1, over 1. And my symbol is less than or equal to, which means I've got a solid line. It's less than, which means I'm shading below this line, but not yet. The middle one, the y is by itself, except the x is in the wrong place. So let's rewrite this to be y is less than or equal to negative x plus 4, so that way we can see what's in the correct place. So again, I have a y-intercept of positive 4. My slope is negative 1 this time, so down 1, over 1. Or up 1 to the left 1. Y is less than or equal to, which means I've got a solid line again, and it's less than, which means below this line, less than, lower, and then I've got one more line. Y is greater than or equal to 0. So you saw the x lines were vertical on the last problem, and y lines are horizontal. And where y is 0 is right here on this y-axis, or the x-axis, excuse me. So if you draw a thick line, solid line, because it is got the bar underneath, and its y is greater than this line, it's got to be everything above this red line. So if you look at all 3 of your lines here and look at where your arrows are pointing, I got to be below the blue line, below the purple line, and above the red line. The only place where this makes sense is right here in this middle triangular section. So there are different ways to solve a system of equations. We looked at graphically and algebraically, specifically using the substitution method today.